Okay, continuing with our unit on limits, we're going to revisit a problem we already know how to solve as a pre-example and getting a little bit of a mindset going into the new stuff for today. So our function that we're considering here is x squared minus 9 over x plus 3, and we are interested with what's the limit as x approaches negative 3. Well, we know something's going on at negative 3 because the function's undefined there. Now, based on our knowledge of rational expressions, we can very confidently predict whether it's going to be a vertical asymptote or whether it's going to be a hole in the graph. So if we factor the top, we realize the x plus 3's will cancel out. If the x plus 3's cancel out, that means that we're going to have a hole at x minus 3, at x is equal to negative 3 rather. Okay, so we know from what we talked about a few days ago in limits that the y coordinate of that hole will answer the limit question. We can find the y coordinate of that hole by plugging that negative 3 into the simplified version. So when you plug in the negative 3, the value we get back is negative 6. So the limit as x approaches negative 3 is equal to negative 6. So what we did here is an analytic approach to evaluating this limit, meaning using standard paper pencil techniques. This could be confirmed graphically, this could be confirmed numerically, both of which would be best done using technology, specifically our graphing calculator, and it does turn out that this checks, but you can do that on your own if you want to verify it. Alright, what we're going to do is think about, well, what did we do? We took an expression that we were unable to plug a negative 3 in directly to, algebraically manipulated to the point where that number could be plugged in, and that answered the limit question. Okay, that's the thought process we're going to be using for the next few examples. So first new thing for today is, get this here, we're going to be dealing with the limit in a complex rational expression. So we're going to make the observation that we cannot plug 0 directly into this expression because this expression is undefined at 0. So what we're going to do is algebraically manipulate this expression to the point where we can plug 0 in, and that will answer our limit question. Well, one of the ways that we deal with complex rational expressions is to multiply through by the common denominator. So I put the 1 over the 1, the x over the 1 to make the visualization easier. The common denominator for 1, and x plus 1 is x plus 1. So we multiply the top through by x plus 1, the bottom through by x plus 1. That gets us initially to here. On the far left, the x plus 1's cancel and leaves you a 1. Upper right, nothing cancels. Bottom, nothing cancels. So up top, we clear out those parentheses. The positive 1, negative 1 cancel each other out. Then, that x and that x can cancel. Slide this up a little bit. And that gets us to the point where we've algebraically manipulated the original expression to the point where that 0 can be directly substituted in. So after you substitute that in, we get negative 1 over 0 plus 1, negative 1 over 1, which is negative 1. So the limit as x approaches 0 is equal to negative 1. So again, we did this analytically. This can be confirmed graphically. This can be confirmed numerically on your calculator. All right, next new thing for today is we are revisiting something we talked about a while ago known as the difference quotient. Okay, the difference quotient is f of x plus h minus f of x all over h. As a reminder, some textbooks, some websites, usually the ones that are a little bit more old school, instead of an h, that would be a delta x. Algebraically, it doesn't matter what symbol is there. For today's purposes, we're going to stick with the simpler h rather than the more complicated to write delta x. Now when we address this guy, whenever that was, a while ago in our rational expression unit, I had said it was a small part of the bigger problem. Now we're going to examine what the bigger problem is. So for these guys here, you are going to be given some function, and then you're going to take that difference quotient and then take the limit of it as h approaches 0. So plugging everything in, f of x plus h means we're going to that function f. The x gets replaced with x plus h. That's the upper left, which is this right here, minus the function as is, all over h. And then after we get that taken care of, we're taking the limit as h approaches 0. So connecting this back to the last two things that I did, the key thought process here is we cannot plug h directly into this expression. This expression is undefined at h. So what we're going to do is algebraically manipulate it to the point where that 0 can be substituted in for h, and that will answer the limit question. So making that happen, that x plus h gets expanded out. Cleared those parentheses. Next step, clear these parentheses by multiplying through by the 2. That gets us to this up top. And then the positive 2x, negative 2x squared, negative 2x squared cancel, positive 1, negative 1 cancel. And in general, you may recall that's typically what to expect with these guys. Usually when you're dealing with the difference quotient, whether it was just a regular rational expression back when we saw it the first time, or now part of a bigger problem, limits, usually what's going to happen is the top will expand out to be rather large and potentially messy, and it should simplify down pretty significantly. Okay, that gets us to here. The method that tends to work the fastest, the most often, is if you have multiple terms on top and a single term on the bottom, divide that into both. That gets you to here. And now we've reached that intermediate goal where we took our original expression that we could not plug 0 in for h, and we've algebraically manipulated to the point where you can plug 0 in for h. So when we plug in 0, we're left with just 4x. Now when you're using the difference quotient, for the general case where that x is actually x, typically for most problems you can expect your final answer to be in terms of x. The next example that I'm going to do for you will have a difference quotient, but instead of an x, there's a specific x value that we're interested in. So for all of these guys, they always have to give you what function it is that you are dealing with. These functions don't have to be quadratic. They tend to be the ones that are typically used for opening examples with this. They're reasonably challenging, but they're not over the top difficult. Now, comparing this to the previous problem, we were using a difference quotient where that x was the variable x. Now we're doing a difference quotient where we have one particular x value in mind for this particular problem 3. So what we're going to do, f of 3 plus h, we're going to function f, replace the variable 3 plus h. That's this right here. Minus f of 3, so that's minus the function evaluated at 3, all over h. Mindset here, we can't directly plug a 0 in for the h, so what we're going to do is algebraically manipulate this to the point where we can do that. So making that happen, this gets expanded out, minus 1 is as is, minus, and then evaluate that numerically. The 9, minus 1, minus 8, they cancel each other out. That gets us to here. Divide that h into both. That gets us to here. And now we've algebraically manipulated that expression to the point where we can plug in 0 for h. So our final answer is 6. Again, comparing and contrasting to the previous problem we just did, what you typically can expect is when you're using a difference quotient where there's the x in the x slot, you expect to have a variable expression as your final answer. Not always, but typically. And if there's a number in that x spot, you expect to get a number back, in this case like 6. Okay, one more example for today. We want the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Here's our mindset that connects all of our problems together for today. We cannot plug 0 in for x. This function is undefined. So what we're going to do is take this expression, algebraically manipulate it to the point where we can plug 0 in for x, and that result will give us the answer to the limit question. Now the strategy we're going to use here is we are going to, instead of rationalizing the denominator, which we know we've done in almost every math class you've taken since Algebra 1, we're going to rationalize a numerator, because in the calculus world this is relatively common, where you get this binomial up top where one of them is a radical. So what we're going to do is take whatever that binomial is, identify its conjugate, and multiply the top and bottom by that conjugate. So this is a binomial times its conjugate, multiply the two first terms, that's a radical times itself, so the square root just cancels out. And then we know the outer inner cancel due to the algebraic structure of what's happening here. We just have to do the L for the last with the FOIL. The -1 times +1 is -1. The bottom, I'm not going to multiply that out. Usually with these problems, it tends to be in your best interest to not multiply it out. If you do multiply it out, it's very often you have to refactor it later, so we typically don't want to do that. Alright, so after the +1, -1 cancel, that gets us to here. Now that x can cancel with the x on the bottom, that gets us to here. And now we've reached that intermediate goal stage that we've reached for the last several problems. We started with an expression that you cannot plug 0 in for x. Now we can plug in the 0 for the x. So after you plug the 0 in for the x, we get a 1/2. So that answers our limit question. The limit as x approaches 0 is 1/2. Now with all of the problems we've done, where the answer was a numerical final answer, you can confirm this numerically, you can confirm this graphically using your calculator. The one that wouldn't have been an option for would be this guy right here. When you're doing a limit question and your answer is some algebraic expression, which happens, one of the ways it can happen is when you're dealing with a different quotient and a limit where that x stays the x. Okay, based on the math we know in this class, that one we can't check on a calculator. But all the rest, where it's a numerical final answer, they can be checked on your calculator. As a reminder, numerically, what you would do is set up a table of values in your table. Graphically is you would look at the picture of the graph and identify how it's tracing from the left and to the right.